So there are many different types of functions that I'm sure you've seen in algebra and calculus courses. You kind of you study the whole range of functions: linear, quadratic, cubic, exponential, all those things. But here we're going to sort of look at the concept of functions in terms of some of the stuff that we've done previously. Not too many things, just a couple of them that are kind of interesting that you might not have seen in other classes. Okay, so let's go back to this concept of cardinality of sets. Okay, so two sets are said to have the same cardinality if there exists a bijection between the two of them. Okay, so we know cardinality is how many elements are in the set. So this says that if there's a bijection between them, then they have the same cardinality, the same number of elements. If a set has the same cardinality as the set 1, 2, 3 through n, so just kind of starting to list the positive integers up to n, we say that its cardinality is n. Right? So this will help us figure out the cardinality of sets that are not necessarily easy to count. Right? So we have finite sets. So for finite sets, we know that they have a cardinality because it's like finite set. You have a finite number of elements, and you can count them, and it's like, oh, that's how many elements are in the set. Okay, so especially with like integers, you can do that. But some sets are harder to figure out if they're countable or uncountable and what the cardinality is. So the kind of these functions are useful to do that. So let's look at another definition. So a countable set. Right, so as I said, if a set is finite, then it's countable. Or if a set is infinite, but has the same cardinality as the same of positive integers, then it's called a countable set. All right, so this kind of might be a little bit counterintuitive. It's like, how can an infinite set be countable? Countable and finite don't mean the same thing. So a set doesn't need to end or have a finite number of elements in order for you to be able to count them. Okay, so if it has the same cardinality as the set of positive integers, that basically means that you can count them: the first element, the second element, the third element. So you can sort of there's some counting going on there, right? A set that's not countable is called uncountable. So we have this sort of division between countable and uncountable sets. Okay, so we have countable sets is one category, and finite sets are countable. Okay? But for infinite sets, so infinite sets that has a one-to-one correspondence, that it has the same cardinality as the same set as the set of positive integer, are called countable. So have the same cardinality as the set of positive integers, then you call those countable. Uncountable sets are the other ones. Uncountable sets are infinite sets, okay, which means they have an infinite number of elements in them that do not have the same cardinality as the positive integers. Okay. All right, so next bit here is going to help us figure out how do you check? How do you check that a set has the same cardinality as the set of positive integers? And it's typically through forming a bijection. Can I form a bijection between my set and the set of positive integers? And then that will show that they have the same cardinality. So another just concept here or notation, when an infinite set is countable, we denote the cardinality by this symbol right here. This is Aleph null. Aleph is the first letter in the Hebrew alphabet. This is like the capital A, basically. If the set is finite, you give its cardinality to be a number, a positive integer that tells you how many members are in that set. If the set is infinite and countable, you say that its cardinality is Aleph null. So here's an example. Let's show that the set of integers is countable. Okay, so to show that the set of integers is countable, we need to show that it has the same cardinality as the set of positive integers. Okay, so we need to show that the set of integers has the same cardinality as the set of positive integers. Okay, to show that, we want to show that there's a one-to-one and onto correspondence between these two sets. Okay, so basically we need to have a function that goes from the set of positive integers to the set of integers that is a bijection. Okay, right, so let's see if we can do that. Let's list like a few things, right? So basically my domain is the set of positive integers. So my domain for this function is not 0, 1, 2, 3, 4, 5, and so on. Okay, so that's the set of positive integers. And I want my range to be, the outputs, I want it to be the set of all integers, positive, negatives, and 0. So ... -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, and so on. Okay? So how can I go from the domain to the range in a one-to-one correspondence? Okay, so one way of doing it, this sort of a little bit, we can come up with a function pretty easily, okay, is to pair up all the even numbers in my domain with positive integers and all the odd numbers in my domain with negative integers. Okay, so it's a good split, because you can sort of, the range has like two natural groups and my domain is only positive values, so it doesn't seem to kind of fall into two natural groups. But even in odd stuff, it's basically like half are evens and half are odds. So it kind of makes sense that you can pair them up this way. Okay, so let's have the even numbers in the domain pair up with positive integers in the range, and odd numbers in the domain pair up with negative integers in the range. Okay, so basically 2 would pair up with 0, 4 would pair up with 2, 6 would pair up with 4, and so on. Okay, and then let's see if I can find another good color. The odd ones, okay, positive integers. I've been skipping too many. Let's backtrack a little bit. Okay, so let's try that again. So even numbers in the domain pair up with positives. Okay, so the 2 would pair up with 0. Let's include 0 as a positive. Okay. 4 would pair up with 1. 6 would pair up with 2, and so on. So basically we want to account for all elements in the range, okay? All right, and the odd values in my domain, in the set of positive integers, are going to pair up with negatives, okay? So 1 would pair with -1, 3 would pair up with -2, 5 would pair up with -3, and so on, okay? So let's see if we can come up with a function that shows this pairing. Okay, so obviously we want to come up with a function that's going to be piecewise, right? We're going to need a function definition for positive integers, n is bigger than or equal to 0, and a function definition for n is less than 0. Okay, all right. So let's look at the positives. Okay, so I did that in green. So let's pull up a green color again. All right, so what I paired up was like the evens go with the positive. So like 2 pairs up with 0, and 4 goes with 1, and 6 goes with 2. Okay, so notice that for each, this go by 2s and these go by 1s, so it looks like it's going to be a linear function, right? Like 8 is going to go to 3, and 10 is going to go with 4. So the slope stays the same. So this is going to be a linear function. We just need to figure out the slope and the y-intercept, right? So if I say f of n is going to have a slope of 1/2, because we're going up by 1 here over 2 by here, all right? And we want to make sure to start it in the right place, right? So when n is 2, this has to be 0, so that has to be -1, okay? So for this to work out, right, we need this function right here, right? So let's see, when n is 4, we get 2 minus 1 is 1. When n is 6, we get 3 minus 1 is 2. Okay, so basically you take half of the input, subtract 1 from it to get this pairing to work out, right? So good, I have 1/2 n minus 1 is my function formula. All right, now let's look at the negatives. Okay, so let's look at the negatives. So odds in my domain go with negative integers. So 1 is going to go with -1. 3 is going to go to -2. 5 is going to go to -3. 7 is going to go with -5. Okay, so same idea. Let's figure out a function. It's linear, because as I'm increasing this by 2, this is going down by 1. Okay, so the slope is going to be -1/2 n. All right, and let's see if we need to add or subtract anything. Right, if I input 1, then I should get -1/2. I think I need a -1/2 in here, right? If I input a 1, I get -1/2 plus -1 is 1. If I input 3, -3 over 2 minus 1 over 2 is -2. Okay, so this works. Okay, so this right here is -1/2 n minus 1/2. Okay, so I have this function that I built that goes from the domain of positive integers to the range of all integers. Right, if I can show that this function right here is a bijection, then there's a theorem that says that the cardinality are going to be the same, right? Because a bijection means that there's a one-to-one correspondence. Okay, so bijection means that this is going to be 1-to-1. So each element in the domain goes to an element in the range. Okay, so 1-to-1. Okay, and it's a straight line, so that's going to be true. It's no way that you can have more than one value of x going to one value of 1, because each of these pieces are linear functions. So it's 1-to-1. Is it onto? So onto means, are all the values in my range of my codomain used up? Am I accounting for all of them? Okay, so again, it is onto function because as I'm going sort of larger numbers, more positive, more negative, I can keep going. I have an infinite number of even values and odd values that I can connect them with. So this is onto. Okay, so because this is a bijection, this means that the cardinality of z plus is going to equal to cardinality of z. Okay, and the set of integers is countable. Set of integers is countable. All right. All right, let's look at another example, same type. Show that the set of odd positive integers is countable. So again, we're trying to see, let's see if I can find a function which is a bijection between the set of positive integers and the set of odd positive integers. I'm going to call it O plus, all right? And if you can find a bijection between them, then you're going to say that these sets have the same cardinality, and because we know the set of positive integers has Aleph null cardinality, that's somebody proved that theorem, then the set of odd integers is countable. Okay. All right, so let's kind of list our domain. So just as before, the domain is positive integers. So 1, 2, 3, 4, 5, 6, and so on. Okay, and my range is going to be the set of positive odd integers. So 1, 3, 5, 7, 9, and so on. Okay, all right, so let's see. We're going to just match them because there's no positive and negatives. We're just going to say 1 goes with 1, 2 goes with 3, 3 goes with 5, 4 goes with 7, 5 goes with 9, and so on. Okay, so now let's see if we can find a function for this relationship, right? So this basically in the domain are my x values and the range are my y values in this function. Okay, so let's see if we can figure out a formula. Okay, so because if you're looking, these go up by 1 and these go up by 2. Okay, and this is like a constant. This is a linear function because it has a constant slope. And the slope of it is going to be 2 over 1. So the function is going to be 2n, but we got to make sure that it's sort of, we have the right y-intercept, right? So when n is 1, this has to be 1, so we got to subtract there, subtract the 1 there. So yeah, when n is 1, then the output is going to be 1. When n is 2, 4 minus 1 is going to be 3. Okay, so here's my function right here. And this shouldn't be a surprise that it looks like it's a 2n plus 1 just because we started with a 1 instead of a 0 for a domain, but this is a odd number. 2n minus 1 is kind of the definition of an odd number. So now the question is this a bijection? Okay, so we're thinking this is a linear function, it's a straight line. It is going to be 1 to 1, right? If you graph a straight line, right? It's a 1 to 1 function. It's not going to have same y value for 2 different values of x. And it's also onto, okay? Onto means that all the odd integers are going to be outputs for this function. Okay, so I'm not going to have odd integers that are unaccounted for because I can always sort of plug in the next integer, positive integer, in line in this function to get any odd integer out. So they're 1 to 1 or onto. So this means that the set of positive odd integer is going to have the same cardinality as the set of positive integer, so this is countable.